So maybe you are familiar with these 20 questions. So in Korean we say questions maybe. 20곡. So this is a game that you can play with your friend. You have something, maybe some word in your mind, and your friend has 20 questions to guess what you are thinking. And your answer will be always yes or no. Maybe your friend first say that, is that the thing that you are thinking, is that an animal or plant, something like that, and you can say, is that an animal? Then you can say, if you're thinking of a cat, then you can say yes or no. So your answer is yes or no. And after or within these 20 questions, if your friend guesses the correct answer, then he wins, or he or she wins, and otherwise you win. That's a kind of famous game. And is this easy or not? Is it easy or no? Is it easy to guess or no? Because 20, even though the answer is always yes or no, you have the thing that you have 20 questions. There are many choices that you can make. So in fact, 2 to the 20 possibilities of this outcome of this 20 questions problem. So we will see, and this kind of question can be described in terms of binary trees. So first question, you have something like question number 1. The output could be yes or no. So there are 2 possibilities. For each question, you have different. For each output, you have different questions, and each question you have 2 outputs like that. So after 20 things, we have many outputs in the terminal vertices. This is how we describe this game in terms of tree. And let's look at a simple, more specific question. So 5-coin problem. So the situation is as follows. There are 5 coins, one of which is either, one of the 5 coins is a fake one, say. So it's different. The weight is different. It's either heavier or lighter. The other 4 coins have the same weight. Then is it possible to find the different one, different coin, and also not just determining that this is the different coin, but also and determine whether it's heavier or lighter. It's heavier or lighter. Is it possible? Oh, of course, we have to keep some conditions by using a pen balance. Just twice. So pen balance is like this. You have 2 pens like this, something like that. I don't know. So you put some objects on one side and another object on the other side. It will tell you whether they have the same weight, or this left one is heavier than this or lighter than this. It only tells you this. Doesn't tell you how much is heavier or lighter. Just tells you this is heavier or this is lighter, or they are equal. Can you do that by using this only twice? So we need only 2 comparisons. So let's say C1, C2, C3, C4, C5. These are the coins. Let's name them 1, 2, 3, 4, 5. So one of them will be the fake one. And so here at the first trial, first comparison, you will compare two sets of coins. You don't have to have just one coin and one coin. You can have either 2 versus 2, or even like 3 versus 2. Maybe, of course, that doesn't really help you. So first, you have some comparison, right? So just you don't decide how we compare two sets of coins just yet. Just imagine that we have something comparison. Then how many outputs do we have? You have maybe a set A. A is a set of coins among this. B is another set of coins. And then you will compare this pen balance. Will compare the total weight in A and total weight in B. And it will tell you only 3 things, right? There are only 3 outputs, right? Either the left one is heavier, or they are equal, or the right one is heavier. It will only tell you 3 things, okay? And for just imagine that we can determine the answer by using a pen balance only twice. Then we have some strategy. By saying that we can determine this means we can always determine, no matter what situation we have. Okay. If you are lucky, if you do this sometimes if you cannot do this, then that doesn't mean that. Then we don't say that we can determine this by using the pen balance twice. So in this case, we will do comparison 2. The second round. But of course, it may depend on the output of this. You don't have to compare the same set of things over here. You have different set of coins here, here, and here, here, like that. And it will also give you 3 outputs at most, right? It only tells you. And right here, you have already used 2 comparisons. So you have to now decide which one is the fake one and whether it's heavier or lighter than the others, right? Then here, how many outputs do we have? 9 outputs, right? But can we decide any situation? Because these are arbitrarily given, so output would be something like this. Must be of this form. B, something like this. Ci, maybe a pair, Ci and some letter, heavier or lighter, right? Output should be always like this because we want to decide which one of these coins is the fake one and whether it's heavier or lighter. So the answer, output must be like this. In this case, okay, C1 is the fake one and it is heavier than the others. And here, C1 is the fake one and it is lighter than the other, etc. Then how many outputs do we need here? Because either we can, maybe C1 would be the fake one, or C2, C3. They could all be fake ones because we don't know which one is the fake one yet. So we need at least how many outputs? 10 outputs to decide all possibilities. But if you use pen balance only twice, all possible outputs will be just 9. So you cannot really decide the answer. You cannot decide this problem just using the pen balance twice, because the number of outputs that we need is bigger than the number of outputs that we can produce by this tree. So it's impossible. Is this okay? No matter what strategy you have, it's impossible. Another example. There are 9 coins, and one coin is lighter than the other. the others. So 8 coins, they have the same weight, and 1 coin is lighter than the others. Then we use pen balance twice. Can we decide the coin which is lighter? Now we have more coins. In the previous example, we had 5 coins, but we couldn't do this. But in this case, because we know additional information that the fake one is lighter than the other. So lighter, we know it's lighter. So in this case, you know, if you use pen balance twice, there are 9 outcomes, right? Possible outcomes. Outputs. There are possible 9 terminal edges, and possible outcomes. Because we have C1, C2, Cn. After twice, 2 comparisons, you can say Ci is the fake one. So the possible outcomes will be 9. C1, C2, C. So 9. Because you can say C1 is the fake one, or C2 is the fake one, etc. So there is a possibility we can really have a good strategy to determine this. But the number, just counting these numbers doesn't mean that you can always do this. In order to do this, we really have to find a strategy. Because this only tells us that there might be a possibility. But actually, in this case, we can do this because, you know, just divide this into 3 piles. Like, first compare C1, C2, C3, and C4, C5, C6. And there will be 3 possibilities, right? So the left one is heavier, or they're the same, or the right one is heavier. So in each situation, in each output, we have some situation. What does this mean? This one is heavier than this. What does that mean? We know at least one of these is the fake one, because if not, they would be the same. And we know that the fake one is lighter, so they are all normal ones. The fake one will be one of these. Is that right? Because this one, the fake one will be somewhere here. And now we know that one of these is the fake one, so we can just compare just 2. C4 and C5, and we have 3 possibilities, like this or this or this. What does this mean? C4 is heavier, this is lighter, then of course this will be the fake one. So we say that C5 is the fake one. We can conclude. What if they are the same? They are the same, that means they are normal. But we know from this previous comparison that there must be one fake coin here, but we know that they are not C4 and C5. That means C6 must be the fake one. And finally here, this one is lighter, so C4 will be the answer. What about this? They are the same. That means the things that we didn't compare, fake one must be one of these. So we compare C7, C8. There are 3 outputs, this or this or this. If this one's bigger, the C8 is the fake one. If they're the same, C9 must be the fake one. This means C7. And finally here, this means this is lighter, so we must have something over here. So C1 and C2, and we have 3 possibilities, this or that. This means this is the light one. Same means C3. This means C1. So we can always decide. Okay. So indeed, it is possible. using this strategy, you can always determine the coin with light weight. So finding the number of terminal vertices in a binary or tree like this can be useful to analyze the complexity of an algorithm. So one of the basic but very important algorithm is sorting algorithm. Sorting. So let's see an example. Let's consider an algorithm to sort three distinct numbers. Say A, B, C. A, B, C are distinct real numbers. So we want to decide which one is the smallest and which one is the second smallest and the largest. But for sorting algorithm, we just compare two things. It's not like a 10 balance. We don't compare a bunch of letters and a bunch of letters. You just compare always two numbers. And it will only tell you whether this one is bigger or smaller. We assume that they are distinct, so if you compare two numbers, there will be only two outputs. Either the first one is bigger or the first one is smaller. So suppose we compare this. Let's say this. Compare this. I mean, think of this as a question. Is A smaller than B? Then there will be two answers, possibilities. Either the answer is yes or no, right? Yes or no. Yes, that means this is true. Then now we compare B and C. And the answer would be yes or no, right? If yes, what does that mean? A is smaller than B, B is smaller than B is smaller than C. Then we can the sorted sequence will be A, B, C. These are in this increasing order then. Okay. What about if it's no? That means no, B is bigger than A and B is bigger than C. Then we cannot decide just yet. We cannot sort. We cannot finish sorting. We have to compare C and A in this case. So is A bigger than C? We ask this question, and the answer would be yes or no. If it's yes, that means A is the smallest, C is the second smallest, B is the largest. But let's use A, B, C, B. No means C is the smallest, and A and B, like that. And if now we have finished it here on this side, and here B is now smaller than A. B is smaller than A. Let's compare A with C. Then answer will be yes or no, right? Yes, if answer is yes, A is smaller than C, and here, because the answer was no, B is smaller than A. So the sorted sequence will be B, A, C, right? And what about here? So this means A is bigger than B, A is bigger than C. So A is the largest, but we don't know whether B is bigger than C or not. So we compare B and C. B, C, then yes or no. If it's yes, B is the smallest, and then C, and then A. Otherwise, C is the smallest, B and A. So how many comparisons do we need here in the worst case? Here first, and the second, and the third. So 3 comparisons. Is there a better way to do this? Can we sort a sequence of 3 distinct numbers by doing only 2 comparisons? It's impossible, because if you have just 2 comparisons, the terminal edges, terminal vertices will be 4. you know, first comparison, second comparison, we have 1, 2, 3, 4. But how many possibilities do we have? Sorted, if you sort A, B, C, there are 3 factorial permutations of this, which is 6. So we need at least 6 terminal edges. So it's impossible. So this is the best possible, best algorithm in that sense, because you cannot reduce the number of comparisons in the worst case. But sometimes if you are lucky, you can sort this by doing only 2 comparisons, but in the worst case, we need 3. So for 3 distinct numbers, 3 number of comparisons is the best. But what if we have general n distinct numbers? How many comparisons do we need in the worst case? We can do this using the binary trees and analyzing the terminal vertices. Let's say Fn is the number of comparisons needed to sort n numbers. In the worst case of a sorting algorithm. We don't specify a sorting algorithm. Just imagine any sorting algorithm. When you have a sorting algorithm, then in the worst case, we know how many times we have to compare 2 numbers. Say that Fn is that number for a given sorting algorithm. Then we say that Fn is omega of n log n. Omega means big O and big theta, right? Big O. Oh no, it's not. Theta is the exact number. This means Fn must be at least of order of this number. This is like Fn is greater than or equal to C times n log n. It must be at least as big as this number. So you cannot find an algorithm that compares less than this number. So we need at least this amount of number. So how can you prove such a thing? Proof. Basically, the proof is the same as the argument that you used over here. You just consider all possible outcomes and compute the number of possible terminal edges. Terminal vertices. So let's say A1, A2, dot dot dot, AN. These are the distinct numbers that we want to sort. Distinct numbers. The possible outcomes are what? Because they can be in any order. We don't know which one's bigger just yet. So possible outcomes would be just permutations of them. Possible outcomes are the permutations of these numbers. But how many permutations are there? N factorial. So number of possible outcomes is n factorial. But let T be the comparison tree. When you have an algorithm, that means we have a comparison tree like this, because we only have to compare 2 numbers at a time. So at the first comparison, we compare 2 numbers, and then for each output, we compare another pair of 2 numbers, etc. So having an sorting algorithm basically means we have a sorting tree like this. Comparison tree like that. Then what is the number of terminal vertices in T? By the way, the sorting tree means you have something like that. But this is these are the levels of comparisons, right? So what is the level of comparisons here? At most, not exactly f of n, because that fn is the worst case. The number of comparisons is the worst case, right? What is the height of this tree then? What is the height of tree? Height equals, that's fn, because the height of this is 0, 1, 2, 3, etc., and then the height of this will be fn. The height of this tree will be the height of the this lowest terminal vertex, which is fn. So yeah, but we know the number of terminal vertices, this must be greater than or equal to 1. Because this is a sorting algorithm, we have to decide, we should be able to get any possible output. That means must be at least n factorial. Because otherwise you cannot, some permutation will be missing. That means you cannot sort that situation. Then because we have this theorem, if this is a binary tree, T is a binary tree with height what? Fn. When you have a binary tree of height h, what is the maximum number of terminal vertices? 2 to the h. There we have a theorem. So number of terminal vertices is at most 2 to the fn. Okay. But then this, we know that this is greater than or equal to n factorial, so that means n factorial greater than or equal to 2 to the fn. If you take the log base 2, we get log n factorial greater than or equal fn. But from here, we know that this is theta of n log n. We learned this in a few months ago, right? So this means fn is at least the order of n log n. You cannot perform better than this. So if you have an algorithm that gives you at most n log n times some constant number of comparisons, that can be an optimum algorithm for sorting a sequence. There are many algorithms with this performance. Is this okay? All right, then let's move on. Section 9.8, Isomorphism of trees. So we learned isomorphisms of graphs. So let's review them. So two graphs, G1 and G2, these are isomorphic if basically this G1 can be obtained from G2 by relabeling the vertices. It's like this. 1, 2, 3, 4. This is isomorphic to this graph A, B, C, D, because relabeling means you have a function, a one-to-one onto function or bijection from the vertex set of V1, G1, to the vertex set of V2. This means, in other words, the bijection such that U, V is in an edge set of E1, the first graph, if and only if their images are adjacent in the other graph. So in this case, how can you find the bijection? F1, you said F1 equals, maybe F4, you can focus on F4. 4 is the vertex of degree 1, only vertex. So we should say send this to C, and the other thing can the 3, no, we have to, 1 should go to B or D, F2 should go to D, F3 should go to A. It's like that. And this is a bijection, and we have 2 vertices adjacent if and only if their images under F are adjacent. So after relabeling, they look exactly the same thing. That's what isomorphism means. But what about trees? Trees are graphs, so we can also consider the same isomorphism on the trees. Since trees are graphs, we can also consider tree isomorphisms. Two trees are isomorphic if they are isomorphic as graphs, right? So, for example, this graph, this tree is isomorphic to this tree, right? You know, we can just say this is the same vertex as this, they're the same. And this is not isomorphic to this. If you want to show that two graphs are not isomorphic, you need to find an invariant. Invariant means some kind of property of a graph, such that every graph isomorphic to that graph must have the same property. If that happens, then that property is called an invariant. So one of the simple invariants is the degrees. Here we have a vertex of degree 4, right? Here the vertex, we don't have any vertex of degree 4. But the degree sequence is an invariant, so they are not isomorphic. Degree always less than 4. So, yeah. In general, deciding whether two graphs are isomorphic or not is a difficult problem. If two graphs are very complicated, if the number of vertices is large. But if the number of vertices is small, then we can, for trees, we can list them. Let's list all non-isomorphic trees with n vertices. For small n, if n is large and small, like 1, 2, 3, 4, 5. So first, n equals 1. Only 1, right? One vertex is a tree, n equals 2, it's just this, right? There's only one tree, isomorphic. Every tree of vertex 2 with 2 vertices will be isomorphic to this. What about n equals 3? Yeah, still we have this, right? You know, these three, they're the same. They're only one structure. N equals 4. We have this straight tree and this. They are now different because this vertex has degree 3 and this vertex doesn't have anything. But are there anything else? In this case, they are all possible non-isomorphic trees. N equals 5. Straight tree, 3, 4, 5, and 1, 2, 3, 4, 5 like that, and 1, 2, 3, 4, 5 like that. I think these are all. There are 3 non-isomorphic trees with 5 vertices. But can we actually show that they are all? Maybe you can consider degrees. Here, degree, what is the maximum degree of, consider maximum of the degree. Max degree equals, here, what is the max degree? If the max degree is 2, it must be a path like this, right? You cannot, because you have to go only one direction if you start with this. Max degree 2, this is the only one. Max degree equals 3, then that means we must have something like this, right? And we have one more vertex, but you cannot connect that to this. And this is only, but you know, if you connect this to here, 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 they are all the same, isomorphic. So you have only one thing. It's only one thing. Max degree equals 4. This is the only thing, because you have to connect the 4 vertices to the single one. And max degree cannot be 5 or more. So there are only 3 possible. You can list the trees, non-isomorphic trees with 6 vertices and 7 vertices, but they get more and more complicated. So in general, it's not an easy problem to list all the non-isomorphic trees. But for small n, we can list them like this. So for trees, just simple, we don't have any new concept because we just borrow the isomorphisms from graphs, because trees are graphs. But we now consider some more structure on trees, like a rooted tree. And we can consider the isomorphism of rooted trees. Say T1, rooted tree with root R1. T2 is a rooted tree with root R2. And we say that they are isomorphic. We say that T1 and T2, these are isomorphic if there is a bijection F from the vertex set of T1 to the V of something means vertex set T2, such that first we want to keep the root. The root must correspond to the root. So F of R1 must be R2. We want to make a correspondence between the root. And second, that's the same thing as the previous definition. So U, V, these are adjacent in the first tree if and only if their images are adjacent in the second tree. So without the first, if you just forget about the first condition, then it's the same as the isomorphism of 2 graphs. So for example, this tree, rooted tree, so I'm gonna put the root at the top. Like that. So 1, 2, 3, 4, 5, 6, and 7. This is isomorphic to this tree. A, B, C, D, E, F, G. How can you find an isomorphism? F is called isomorphism. Let's use phi here. So phi, of course, the root must correspond to the root. So this must be A. What about this? 2 could be one of these, but we don't want this to be B or D. We want this to be C, because you can see this path of length 2 should be the path of length 2, so this should be C. Phi of 3 or 5 must be E. Phi of 3, this is the vertex of degree 3, so it must be D. Phi of 6 must be one of these, F. Phi of 7 must be G. Phi of 4 must be B. So this is a isomorphism that satisfies both 1 and 2. So basically, trees are isomorphic if you rearrange the children, then you will have the same shape. So for instance, just try to move these children all the way to the right, then you get this, right? Just move this to the right, and they look the same way. So for a rooted tree, that means the two rooted trees are isomorphic if they have the same root, and then all you need to do is to permute the children at each level. And if you permute some children of one vertex, and if you do this several times, and if you obtain exact same shape, then they are isomorphic. Otherwise, they are not isomorphic. So for example, these are not isomorphic. They are isomorphic as trees, but not as rooted trees. They are isomorphic as graphs, but because here we are considering rooted trees, right? If they're isomorphic, the root must have the same number of children. So rooted trees, the number of children is the number of children of the root is must be an invariant. But here, the root has 2 children, the root has 1 children. No. Or the terminal vertices must be invariant, so they are not isomorphic as rooted trees, although they are isomorphic as trees. Not isomorphic as rooted trees. Maybe another example. This is not isomorphic to this. They're not even isomorphic as trees, so cannot be isomorphic as rooted trees either. Again, the degree of the root is different. Degree of the root is 3, degree of the root is 2, already not isomorphic. So let's look at some examples of non-isomorphic trees for small number of vertices. Rooted trees. N equals 1, just 1. N equals 2. Yeah, just we have only 1, right? N equals 3, this or this. N equals 4, straight tree, or this or this. I think they are all. What about this? These two are isomorphic, of course. So we have only 1, 2, and 3. Because you can just think of the max degree of the root. If the just degree of the root is 1, it can be either 1 or 2 or 3, because 3 is the maximum degree. If it's 1, oh yeah, I think I missed one. No, this one more. If the degree is 1, we must have things like this, and then below here we can have either straight tree or this wedge. So there are two rooted trees with root degree 1. Degree 2 must have this. Degree 3, there is only 1. You cannot have a vertex of degree 4. Again, if n gets larger, then it's difficult to consider all of them. So in general, finding all non-isomorphic graphs or trees or rooted trees is a difficult problem. But if you have more structures, then we can find an exact number. For instance, binary trees. T1 is a binary tree with root R1. Binary tree with root R2. And we say that T1 and T2 are isomorphic if there is a bijection F from the vertex set of T1 to the vertex set of T2 such that first R1 equals R2. And second, but what is a binary tree? Binary tree means every vertex has either left child or right child or both or nothing. So we have at most 2 children, but for each child there is some kind of direction. Is it right child or left child, etc. If 2 binary trees are isomorphic, they have the same structure as binary trees. So it means U is a left child of V in T1 if and only if their image is a left child of the image in T2. And third, of course, we change this to right child in one graph if and only if its image of U is a right child of the image of V in T2. So we consider not only just child of something, but we also consider the left child or right child. We want to keep that thing together. Alright, so example. Actually, for binary tree, the isomorphism is, I think, clearer than the others. Other two isomorphisms that we saw. Because they are isomorphic if they look exactly the same. They are the same, but even if you change the direction slightly, they are not isomorphic. Because here, this is a left child, but it's a right child. So for binary trees, trees are isomorphic. That means they look exactly the same. Like this. They must look exactly the same. So you just draw the binary tree, and if they look exactly the same, they're isomorphic. Otherwise, no, they're not isomorphic. That's quite simple. So now let's list non-isomorphic trees. With n vertices. N1, n equals 1, only one binary tree. Oh, sorry, non-isomorphic binary tree. N equals 2, we have either this or this. They are different because this is a left child, this is a right child. N equals 3, we have this. Even the straight tree, there are several possibilities, like this, or this, or this, or this. So there are 4 straight trees, but considering left or right child, they are like this. Are there more? The root vertex may have 2 children. There are 5 non-isomorphic binary trees with 3 vertices. So in this case, you can compute and you can list n equals 4, n equals 5, etc. So in this case, for binary trees, we can find the exact number of binary trees with n vertices, like 1, 2, 5, etc. Actually, this number is a very famous number called Catalan number. Do you remember the Catalan number? So let's review the Catalan number. Cn, usually denoted by C sub n, and this is equal to 1 over n plus 1 times 2n choose n. This is called the nth Catalan number. It has many descriptions. One of them is this. We learned maybe before midterm, I think, or after midterm. We have xy plane, and this line y equals x, and you have a point from 0 to 0, 0, 0 to n, n is an integer, and you want to consider the shortest path, like that, using only up step or right step, east or north, without going below this line y equals x, this kind of path. The Cn is the number of shortest path from 0, 0 to n, such that which never go below the line y equals x. We are not allowed to go below. We may touch this line, but we cannot go below that. And we learn that this is equal to this. And actually, there is a fact. There is a known fact. Cn, Catalan number, satisfies this recurrence relation. C0 equals 1, and for n greater than or equal to 1, Cn is equal to summation I from 0 to n minus 1, Ci, C, n plus, n minus 1 minus I. We have this recurrence relation. I'm not going to prove this recurrence relation in details, but the idea is, so Cn is the number of paths like this. Just consider the first time it touches the line after it leaves the origin. So we don't count this. So after it leaves the origin, it must touch this line because the final point is on the line. You may touch many times. Maybe it's just once at the end or several times like this. Just consider the first time it touches the line after this origin. Then what does that mean? The first step is always an up step, right? And this step must be always a down, like that. And the condition, the assumption that this is the first touch, that means this will never go below this line, because otherwise there would be more touching point over here. And then if this is, say, j comma j, and this part over here, we have one less than this j. So here, think of this as a new origin, 0, 0, and this will be j minus 1, j minus 1. If you shift this down over here, like shift down like that. So this, we can always decompose a path like this into a path over here and a remaining path down there. And this will give us Cn equals, here j is from 1 to n, because j can be any point after 0, 1 to 3 or n. And here we have 1 less than j, so c j minus 1. And here, the length here is n minus j, n minus j, n minus j. So it's c n minus j. They are the same. They are same thing. It's just shift j by 1. If you let I equals j minus 1, they are the same. This is the idea of proof of this relation, recurrence relation. So now we know that the Catalan number has this initial condition and this recurrence relation. Now we can show that the number of binary, non-isomorphic binary trees with n vertices is exactly the Catalan number. So let me state the theorem and prove it. Theorem. The number of non-isomorphic binary trees with n vertices equals the Catalan number Cn, 1 over n plus 1, 2n choose n. Proof. Proof is just this. Let's say an is the number of these non-isomorphic things, non-isomorphic binary trees with n vertices. We want to show that an equals Cn, but we know recurrence relation for Cn. So if we can show that an has the same recurrence relation, then they must be the same recurrence relation, and of course with the same initial condition. Because here the recurrence relation, this determines the whole sequence. You know C0, right? What is C1? If you want to compute C1, everything here is less than the index. Every index is less than n. That means you can determine Cn in terms using the previous terms. It is indeed a recurrence relation. So for instance, C0 equals C1 equals C0 times C0, and that's it, which is 1. And C2, what is C2? I equals 0, then C0 times C1 plus C1 times C2, oh no, which is 2, etc. In this way, you can determine every Cn. So we will basically, our goal is to show that an has the same recurrence relation. First of all, what is the initial condition? A0. Non-isomorphic tree with 0 vertex. The empty graph is, we think of the empty graph as such a binary tree. So we can say A0 equals 1. Now let's say n is greater than 1 and consider an. We want to show that it has a recurrence relation. So let's say T is a tree, binary tree with n vertices. So it has a root. The T looks like this. Root, and it has 2 children, left and right. Let's say T1 and T2. Maybe it may not have a left child. That means T1 is empty. Okay. If it does not have a right child, then that means T2 is empty. We can always write a binary tree like this. Let's say T1 has I vertices. Then what is the number of vertices in T2? If T1 has I vertices. Number of vertices in T1 plus number of vertices in T2 plus 1 must be the number of vertices in T, which is n. So it will be n minus 1 minus I. But T1, this can be any binary tree with I vertices. Then for any binary tree with I vertices, and for any binary trees with n minus 1 minus I vertices, you can just attach them right here and here. Then you will get a binary tree with n vertices. So every tree, binary tree with n vertices, can be obtained like that. Then what is the possible number of possible T1? Because T1 has I vertices, by definition, it is AI. The number of possible T2, A n minus 1 minus I. Okay. Then what happens? I can be which number? I could be 0 because this may not have a left child. So I is from 0 to n most n minus 1 because you cannot have n because of this vertex. That means an is equal to summation I from 0 to n minus 1. Number of possible T1, which is ai, possible T2, a n minus 1 minus I. And because so same recurrence relation as Cn, and of course same initial condition. That means an must be equal to Cn. And this is a proof of the fact that the number of non-isomorphic binary trees is equal to, with n vertices, is equal to Cn.